Hello everyone, my name is Mazen Al-Sabbagh, and in today's topic I'm gonna be speaking about capacitors and direct current. So, what are capacitors and what are their jobs? Capacitors are electric devices that store electrical energy in an electric field. It's similar to a rechargeable battery. It holds power, but it charges and releases that energy much faster. Here is a representation of the physical structure of a capacitor. The device consists of two metal sheets, one with a positive charge and the other with a negative charge. In between them is a dielectric insulator, which could be plastics or ceramics. What process does the capacitor have to undergo? The device is capable of storing energy by capturing electrons from one sheet to generate an electric field, and then it releases the energy stored right away. Here we have an example. Just imagine it like a tank of water, where the voltage is the pressure and charge is the quantity of water, and lastly, capacitance is the size of the tank. Now, I'm going to be explaining the usefulness of capacitors in direct current circuits in real-world situations. We have a camera flash that could be found in phones and cameras. The battery inside the camera charges the capacitor slowly. Then the capacitor stores that energy. When the photo is taken, all the energy stored in the capacitor quickly transfers into the flash tube for the camera to produce the flash used to take the photo. Why does the camera need a capacitor in a direct current circuit? The battery of a camera cannot provide a sudden burst of power. The battery would have to suddenly supply a large current. Real batteries have internal resistance, which means their voltage drops when you try to pull a lot of current quickly. In this slide of the presentation, I've added formulas for capacitance and direct current, and I'm going to be explaining each and one of them, starting with the capacitance formula. The main formula for capacitance is Q equals C times V, Q being the charge, C being the capacitance, and V being the voltage. The charge is measured by coulombs, and the capacitance is measured by farads, and the voltage is measured by volts. We could rearrange this main formula into two formulas, one to find the capacitance and the other to find the voltage. To find the capacitance, we divide the charge by the voltage, and to find the voltage, we divide the charge by the capacitance. On to the second formula, which is the direct current formula, also known as Ohm's law. This formula is V equals I times R, V being the voltage, I being the current, and R being the resistance. And that formula is used to find the voltage. We could rearrange this formula to find the current and the resistance. To find the current, we divide the voltage by the resistance, and to find the resistance, we divide the voltage by the current. Now on to the last formula, which is electric power formula. The formula is P equals V times I. This is to find the power, which is P, and the V is voltage and the I is the current. By substituting Ohm's law, which is the main formula, V equals I times R, and the rearranged formula I equals V over R into our electric power formula, gives us a highly useful formula such as power but using current and resistance, which gives us a formula of P equals I squared times R. And then the second formula is power using voltage and resistance, which gives us a formula of P equals V squared over R. Now we will put these formulas to use and solve three-word problems using them to give you a better understanding on how to use these formulas in word problems. First question, a capacitor has a capacitance of 4.7 microfarads and is connected across a 12-volt battery. What is the total charge stored on the capacitor? I have listed the knowns that we have. The capacitance is 4.7 microfarads, and in this case I have to convert it to farads. So now it is 4.7 times 10 to the power of negative 6 farads. And the voltage is 12 volts, and we are trying to find the charge. So by using our main formula for capacitance, Q equals C times V, I multiplied 4.7 times 10 to the power of negative 6 by 12 to get an answer of 5.64 times 10 to the power of negative 5. Question 2, and Ohm's law is needed for this question. An electric heater has a resistance of 15 ohms and a current of 8 amperes flowing through it. What is the voltage supplying the heater? Our resistance is 15 ohms and our current is 8 amperes, and the voltage is the one we are trying to find. So we are using Ohm's law, which is V equals I times R. Our current is 8 and our resistance is 15. So 8 times 15 gives us a voltage of 120 volts. This is the last question for this presentation. Question 3, using the electric power formula. A laptop charger plugged into a 110 volts outlet draws a current of 1.5 amperes. What is the power consumed by the charger in watts? We have our voltage of 110 volts, we have our current of 1.5 amperes, and we are trying to find the power consumed by the charge. This is our main formula being used in this question, which is P equals V times I, our V being 110, our I being 1.5, substituted in the formula. And then that gives us 110 times 1.5, which gives us our power consumed by the charger of 165 watts. Thank you so much for listening to my presentation, and I hope you understood and enjoyed my presentation. Thank you so much.